Okay, so today what I want to do is share with you what is probably my very most favourite math puzzle. It's a puzzle which I myself have worked on for several years. Many professors and alumni of very elite universities have had a look at it, and no one's managed to crack it at all. So, well, let's hope one of you can. It's a very odd problem. It's not really very traditional. It has to do with self-replication and networks. Let's think about a simple network. We have a load of dots called nodes connected by some lines called edges. And just for the sake of explanation, let's imagine that these vertices represent animals and the edges represent, say, social relationships, maybe food sharing or something like that. Now, this is an idealized mathematical model, so what we're going to suppose is that every springtime, every one of these individuals here has an offspring. And just like a baby comes into the world and forms similar social relationships to their parents, our offspring vertices link to the same things as their parents are linked to. So this is a rule. These are our offspring. And so the rule is basically that when we update, we do this kind of reproduction stage where every vertex has an offspring with the same neighborhood as its parent, and that happens simultaneously. Okay, so this is what's happened so far. We started off with this network here, and then it became this. So we can update it again. Maybe I should just redraw it a little bit more nicely. Now the reproduction. And there we have it. And we can imagine continuing this process ad infinitum. So there are various questions one can ask about these kind of systems, and it turns out that, in fact, in this case, where the network only grows in this way, it's actually fairly easy to understand what's going on. For example, you might want to think about how many vertices there are going to be of a given degree. So the degree of a vertex is just the number of edges touching it. The degree of this vertex is 4. The degree of this vertex is 2. So in general, perhaps you can work out a formula for how many vertices there are going to be with a given degree in this system as it runs. So when we add this death effect, this is when things start to get really interesting, and to be honest, they quite rapidly, in my opinion, go out of, well, certainly out of bounds of what I can understand, and I wouldn't be surprised if some of these problems are like formally undecidable or something. So let's just as a simple model, we'll suppose that there's the reproduction stage. Just every vertex has an offspring simultaneously with the same neighborhood as the parent, just like before. And then there is this death stage. And at this death stage, we shall kill every vertex that has a degree greater than a certain number, let's say d. And we just keep doing these two things alternately. So let's just start with a parameter d equal to 2. We'll call d the degree cap, since it sort of stops the degree getting too big, if you like. So if we just start with this very, very simple one-edge graph here, let's see how it evolves. Well, we do the reproduction stage. No problem so far. And then we do the killing stage. But that doesn't actually affect anything because none of these vertices has a degree greater than 2. None of them have more than 2 connections. So we go back to the reproduction stage. Maybe just redraw this, make it look a little bit neater. And here are our babies. There we go. And so now we do the death stage. We kill every vertex which has a degree greater than 2. So which vertices have degrees have more than 2 connections? Well, this one does, and this one does. So what happens to the network? Well, what happens to it is that it breaks up. In fact, it breaks up into two. Whoops, wrong colour. It breaks up into 2 more of our initial networks. And it also breaks up and leaves behind 4 of these kind of singleton networks. So when we set our degree cap is equal to 4, what happens then? We'll start with the same thing and we'll apply the same rules. So I use coloured arrows. Reproduce. We already know we get this network here. And then kill every vertex with more than 4 links. Well, there aren't any. So we do the reproduction stage again. Now we destroy every vertex with more than 4 connections. And yet again, there are not any. So we go back to reproduction yet again. And it starts to get a little bit difficult to draw, but I think I can hopefully stay with it. So what is this? It's sort of like a box with arms or something. Okay. That's the network on the parents. And now we need to add some offspring. There's our corners. And our sticks. And let's not forget these big hubs linked to lots of things. Okay, so just for clarity then, let me just shade in all these nodes in blue. Oops. I'll shade in the children nodes in blue. And the offspring nodes in green. Sorry, the parent nodes in green. Okay then, so what happens next? Well, we've just done the reproduction stage, but we've still got the death stage to come. So what dies? Well, anything with more than 4 connections. So this baby's gone. This baby's gone. And that's it. I think everything else has less than 4 connections. Remember, reproduction and death occur simultaneously in these systems. So what happens to this great big network? Well, it turns out that it kind of breaks up. Well, no, it doesn't really break up exactly. It sort of opens up. It opens up into a sort of, well, for want of a better word, a butane molecule. And I think actually maybe some bits do snap off. So you see here and here, these nodes, they're only sort of route to the main network is their parents who are dying of, well, if you want to be biological about it, they're sort of dying of starvation. They're having to share resources with more than 4 other individuals. So these nodes are going to end up becoming free floaters. So this particular system produces, well, 2 copies of the singleton vertex, and that'll just keep reproducing itself forever. But what about the rest of the thing? Well, if you think about it a bit, you should notice that it actually turns into a kind of butane molecule like structure. This is the chemical graph of butane, I think. So this is the result of the death stage. We can then apply the reproduction stage on it. And so let's reproduce these degree 3 vertices first. So each of those is linked to the 2 nodes to the left and right of it around the kind of circular structure, as well as the kind of leaf node attached to it. So things are starting to look a little bit floral. How pretty. And also, of course, these leaf nodes are going to reproduce. So we might as well put their offspring inside this floral shape, just like so. Keep things nice and symmetric. So that's what happens after the reproduction stage. So let's just remember what happens. This is reproduction, and then death, which doesn't do anything. And this is reproduction, and then again death doesn't do anything. And this is reproduction. Indeed, we get this nice floral shape. Trouble is, the degrees of some of these vertices are just too damn high. Remember, vertices with a degree greater than 4 are in for it. So, which ones are death marked? Well, it turns out that basically the oldest ones, these 6 kind of hub vertices, these each have a degree 6. Silly me. Yes. Okay, so they're in for it. And so when we do the death stage on this, what's going to happen? Well, a little thought should convince you that what's going to happen is that we're going to end up with um, 6 more of these 6 more of these sort of sticks, if you like. As a result of death. And also we're going to end up with quite a few of these singleton vertices. How many? Let me think. 1, 2, 3, 4, 5, 6. Is that all? Yeah, I think that's all. Just 6 singleton vertices as well. And that's basically a description of what happens in this system. So it's already quite dramatic, even with a degree cap of 4. And perhaps you can imagine, as the degree cap gets bigger, the networks can get larger. And figuring out what can happen is not only difficult, it turns out to be extremely surprising. So if you just cast your mind back to the simpler days when we were dealing with the case where the degree cap was 2, where vertices died just from having more than 2 connections, we could represent that as a nice typed up diagram like this. And here an arrow represents both stages of the update, the reproduction and then the killing stage. Okay, and so using a little diagram like this, we can illustrate all the different things that happen. The one edge network grows up into the 3 edge network, which breaks up into 2 1 edge networks and 2 0 edge networks, which self-replicate each. So that's what happens with degree cap 2, and this is a kind of summary of what you've just seen. Now, I've omitted the drawing of the singleton vertices, the nodes without any edges, just to make things cleaner. But what you can see is that basically, as you keep updating the system, you start with a little line, it grows, it becomes butane, then it makes 6 more copies of the line again, and reproduction ensues. Now, just pause a second and imagine what happens when the degree cap is 6. If you really want to have some fun, grab some pen and paper, try and figure it out. What happens when you start off with a 1 edge network and you keep applying this process of giving every vertex an offspring with the same neighborhood as the parent, and then killing every vertex with degree greater than 6. Well, is this what you expected? It wasn't what I expected. Our single node grows up and grows up and grows up into this kind of butane molecule. Some vertex death has occurred at this point, but and I'm neglecting to draw the isolated singleton vertices. So our initial 1 edge network grows up and it grows up and it grows up into butane, and then it carries on and it persists as this kind of star-like structure. But it doesn't break up yet because our degree cap is higher. In fact, it continues to grow. And then it gets these kind of sort of hooks on the edge, on the ends of these leaves. I mean, one sort of has to invent terminology when talking about such things. And then what happens is it breaks into 6 of these kind of almost cross-shaped structures. Each of those then grows some extra hooks. each of those then grows into this kind of, well, I don't know, let's call it a three-book problem, three-book network. And then that weird thing, breaks up into three butane molecules and one single edge vertex again. So this is bizarre. I mean, again, I'm neglecting showing what happens to the isolated vertices. I want to focus on what's important. But this is bizarre. We're not only getting self-replicating structures, we're getting a natural sort of injection of diversity here. We started off with one self-replicating structure, and now we have two non-trivial self-replicating structures. So, anybody want to hazard a guess what happens when the degree cap is 8? This just blew me away when I first saw it. I mean, you start off with a single edge, and you evolve it according to this mechanism. Give a vertex and offspring the same neighborhood as a parent, destroy a vertex of degree greater than 8, and repeat. And this is what happens. Each of these nodes here represents a different network structure, a connected network. Some of these connected networks, some of these forms that get produced by this sort of ecosystem that bubbles out, some of these forms themselves have thousands of vertices. And there's like over 1,000 non-isomorphic structures, all self-replicating, all that get generated just from starting with a single edge. And when the degree cap is 10, it's even more insane. You've got like 10,000 different kinds of structures that are all self-replicating. And it's computationally challenging to go beyond this point. And so we try to go back to mathematics. Is there enough regularity in these systems to really understand what's going on? Okay then, so here comes one of the open problems. There's actually quite a few open problems about these systems that are sort of interrelated. Here's a kind of, well, I'll call it a weak conjecture, but I mean, if anyone could prove this, it would really be making a great leap towards understanding these systems. So here's the conjecture. Suppose we start with a finite graph and a finite degree capped D. And suppose we keep evolving the system according to our little alternating rule. Reproduce, and then death. The conjecture is that no connected structure can grow, let's say indefinitely. That's easy to understand. Okay, so in other words, let's say as a function of the degree cap, there's going to be some, so say we've got n nodes in our graph and our degree cap is d. So then there's going to be some, if this conjecture is true, then there's going to be some function, let's call it k and d, which basically is such that there's no structure that you can get by evolving an n-vertex graph under this system with degree cap d that's going to go bigger than this number, knd. Basically what I'm just saying is that under these degree cap reproduction systems, stuff can't get infinitely big. This is a conjecture. It might sound a little bit dry, but think about it in the context of those fascinating kind of phase space diagrams from before about what can make what. You see, one of the interesting things about those was that they always turned out to be finite